Moving forward to our next session for liver transplantation, I would request the chairpersons, Dr. Biju Potakat, Dr. Vivek Gupta, Dr. Ramdip Ray, and Dr. Abhishek Yadav to please join us on stage.
So, good afternoon. We are going to listen to Dr. Bersin Eksa, and he is going to present xenotransplantation. How far are we? So, welcome Dr. Eksa to the conference.
Thank you. I hope you can hear me.
Yes, we can.
All right. Let me share my screen. All right. I think you can see the screen and hear me as well. So thank you very much to organizers to invite me to talk about xenotransplantation. So in the next 20 minutes, 30 minutes or so, I will talk about the experience and update and special attention to liver xenotransplantation. These are my disclosures. I hold some patents on xenoantigens, 3D bioprinting, and some data not published yet. So the organ transplantation can happen to anyone, but there are also some certain individuals that we all know, like Steve Jobs got liver transplant, and many others. Only this is the United States. Of course, every country has their own, but you can see the heart transplant and the liver, kidney transplant. So there are so many. So this end-stage organ failure can hit anyone. Dr. Starzl performed the first successful liver transplant in 1967, 55 years ago. And the liver transplant can be very successful, actually. That you can see a 3-month-old girl receiving a transplant 50 years ago and then survived 42 years, and I believe still alive. This article came out 10 years ago when inauguration for Dr. Starzl's award. It's a liver transplantation that Vision realized. And the impact of it could be also really immense, because another article came in JAMA Surgery, Survival Benefit of Solid Organ Transplant, but the more impact came when the Los Angeles Times put this article in more lay terms, saying that 2 million years of life were saved. And this was only within 25 years. Now, considering that we do more transplant in the last decade, and considering in India, in Asia, and in Europe, there are 10 millions or maybe more life saved thanks to organ transplantation. But the situation is very dramatic. This is the wait list in the United States, and globally it's much, much more. So, and every day, only in the United States, 17 people die, and every 9 minutes, every 10 minutes, we add another one to the wait list. So everybody probably saw this chart that we can do more transplant in red. There are more donors every year, but the wait list keep increasing. But probably what you haven't seen is this one. This is the liver transplant wait list. Despite that we do living liver transplant disease, the wait lists do not increase. The reason for it, because end-stage liver disease patients actually die in the wait list, not like a kidney transplant, they are supported by dialysis. So xenotransplantation could be a solution for it, and then if you look at the dictionary explanation, it means for the audience, so they don't know about it, the process of grafting and transplanting organs and tissues between members of different species. In this case, would be from genetically engineered pigs to human. The first xenotransplant in human, successful one, happened in Pittsburgh by Dr. Starzl. Baboon to human liver xenotransplant. A patient survived 70 days slice of infection. Today, we cannot use it, baboon liver, for ethical problems. And if we think that human immunology is one. Of course, the closest species to humans are monkeys, like gorilla, old world monkeys. But if you look at it, pig is more than 35. So there are certain problems immunologically. Before we go through the problems and solutions, why pig organs but not non-human primates? Because non-human primates, there is a concern about spreading infectious disease, and a lot of people still think that HIV came through that. There are ethical issues, limited availability, and poor breeding profile because they also have, like human, only one pregnancy a year. On the other hand, pigs, they are easy to breed, they have large litters, unlimited supply. The pathogen-free pigs actually now easy to breed. Pig organs and sizes are very similar to human, and risk of infectious disease are less compared to non-human primates, and they have already killed millions of them for food purposes, so there are fewer ethical concerns. 5 years ago, we organized in the IXA the theological symposium for the three large religions in the United States. A Jewish leader was there, a Catholic leader, a Muslim leader. So they all agreed that pigs as tissue and organ donors can be used for life-saving procedures. So after a year, the article also came out in Xenotransplantation. So there are certain barriers, of course. Not everything is good that you can take the pig liver and then transplant it. There are immunological barriers that mainly xenoreactive antibodies, and especially in case of liver transplant, coagulation proteins come from the liver, and cellular immunity, as of now, is less of a concern because of the immunosuppressive regimens that we have availability. So advances in xenotransplant happen thanks to two things: with genetic engineering and co-stimulation blockade. A few years ago, I put two articles showing that what genetically engineered pigs are available to research, and there are so many of them. This is just an example. That the list is actually bigger than that. There are currently like 40 different ones, and multiple genes, 10 genes, 15 genes, animals are available. So almost 10 years ago, CRISPR changed this, making in a more rapid way. The zinc finger nuclease technology used to take a lot of time. But on the other hand, CRISPR, here you can see that cuts the DNA in many more regions, and the technology much faster to do genetic engineering, and you can control a lot of things. So you can do the selection of the knockout cells, enrich cells, and then create the pregnancy with somatic nuclear transfer. And from cells to full-term pregnancy, you can obtain pigs in 135 days, so less than 5 months. In the past, this used to be 3 years and kind of a non-selective fashion, so it was very difficult to also get the genetically engineered pigs. Right now, you can actually have different genetics in the same pregnancy, again, less than 5 months. So a little bit of history, and then genetically engineered pig used for the first time in early 2000, it first expressing human CD55. This is a complement regulator protein. You can see that with the genetically engineered pig kidney transplant, it was 80-day survival compared to wild-type ones, only 40 days and less. And I was a part of this trial in Italy during my training. Also, we had a 90-day survival using the same pigs and the same immunosuppression regimen, but still it was limited. Then the group in the United States obtained the GAL knockout. The GAL sugar was knocked out, or the other name is GGTA1 gene. Alpha-1,3 galactosyltransferase gene knockout animals came. Even though the survival was not long compared to the previous experience, it was more consistent, and that's why the article came in January 2005 in Nature Medicine. The group in Canada and Pittsburgh, using the same animal, published again in Nature a few months later that they are failure. So it's only 16 days survival instead of 80, 90 days. The reason for it is a non-GAL antigen. So it was a discovery the problem occurred because of the other antigens. So knowing these, there are other antigens. Indianapolis, we created triple knockout pigs. So GAL knockout, mu5GC antigen, and SDA antigen with different genes. So my previous chief, Dr. Techler's lab, actually created this. Having this triple knockout animal available, so there was a study done using Birmingham Transplant Center's kidney transplant wait list, so the humoral reactivity for IgM and IgG binding. So the desired for human is in this square, so less than 1,000. So, but you can see that with wild type is much higher. What is 1 gene knockout, 2 gene knockouts, and 3 gene knockouts is much closer to human, and that is what now it's a kind of norm that triple gene knockout should be used in clinical trials. In fact, using these animals, kidney transplant survival has extended significantly. It used to be first only 90 days, if you remember. Now we are talking about almost 2 years. But of course, here the costimulation blockade, anti-CD154, or the other main anti-CD40 ligand was used, and then that was the impact of it as well. I was asked to talk almost a year ago the impact of co-stimulation blockade in solid organ and islet xenotransplants in IPTA meeting, and I'd like to show that this is a seminal paper, 900 days survival in heterotopic heart xenotransplant. It's an immunological model, and you can see that there's an induction as well as a maintenance. This anti-CD40 this time was used. The reason for that anti-CD40 ligand has some complications like stroke in humans, so it was stopped and it's not FDA approved. This paper came in 2016, and in 2018, using the same immunosuppression protocol, the German group this time used the life-supporting heart xenotransplantation, and the goal was to get 6 months survival, and they achieved that actually in certain animals, number of animals. You can see here more than 200 days. So that was actually the base study that you may have heard that heart xenotransplant happened in human this year, early this year. So I'd like to show you that as well. So before we go, some just recent news. In one case, I'd like to show you also, because of the audience, also liver xenotransplantation. So we published that actually several years ago, which patients might benefit in a special article in Transplantation Journal, the bridge to allotransplantation in case that acute liver failure happens and then you still don't have the human liver. And we came out with some proposed inclusion and exclusion criteria at that time. I also looked in the past the world experience of genetically engineered pig to non-human primate, and this is our experience. It's 10 animals that time. At that time, it was only GAL knockout and 2 genes animal were available. The longest survival at that time when you do orthotopic transplant was 6 to 7 days, and in one case they had 8 days with non-clinically applicable immunosuppression protocol. It was very heavy. But if you do auxiliary, you can go up to almost 2 weeks that time. And we also showed that there was no hyperacute rejection when you use the genetically engineered animals. This is a liver biopsy from the animal just before the abdominal closure. You can see that everything looked fine. We, of course, studied very carefully the liver function test, coagulation parameters, porcine coagulation factors, because now it's the pig liver in it, and then liver protein production, as well as the specific liver proteins. And I'd like to show you some examples. Like it happens in human, because of the ischemic reperfusion injury, the transaminases go up and then come down to normal within a day or two. INR has been also very stable, less than 2 throughout the study. We look at the many coagulation factors. This is an example with the half-life, very short half-life, factor 5. So you can see the normal human here and the normal baboon. They are very similar, but on the other hand, pig normal is actually very high for factor V. Immediately after transplant, in the baboon blood, we can detect the pig factor V. It's very high. We specifically look at the pig proteins in baboon plasma, since they come from the pig liver. But you can see that the antibody we used was very specific. All these are the proteins that are produced by the liver, very specific to pig. On the other hand, baboons did not detect. And after the transplant, everything comes from the pig. You can see it was a faint first day albumin, but it's very strong, and as well as the other proteins. But the animals started having severe thrombocytopenia. The platelets were gone from the circulation. And we look at also very quickly, this happened as quick as 1 hour after reperfusion. We looked very carefully why this happened in several certain studies. Most of the time we've seen that this is a liver biopsy with confocal microscopy. These are the sinusoids, and you can see the red platelets and the green PBMCs. They clump in the sinusoid and then basically injure the liver. I also looked at all the other organs, so they usually clump in different organs as well, and then create spontaneous bleeding, so that we don't have a long survival. Again, in Indianapolis, with this in mind, with thrombocytopenia, how to avoid it, the IASGCON knockout pigs are created. This is a liver perfusion study using those pigs. You can see that compared to wild type, more platelets stay after this is only 2 hours perfusion, very significantly. And then also the same group, Dr. Tecker's group, also looked at time the other genetically engineered pigs' livers in the perfusion study. Better that your genes are, the more platelets remain in the circulation. This is only 50 minutes, but you can see that almost 50% stay compared to wild type, only 10% stay at that time. Then the group in Harvard, MGH, a friend of mine, Dr. Wagafi, did this study with others. Although that the survival was only 7 days, you can see here, day 4, day 5, they showed actually here the longest survival was 7 days. They used the human coagulation factors that they give externally. And then in the study, they conclude that platelets spontaneously recovered, TMA prevented, and then 66 less blood transfusion need. But again, the survival was limited to only 7 days. So with the same protocol, what they changed is that anti-CD40 instead of the other immunosuppressive regimen, so they used co-stimulation blockade, and they got the longest survival in the liver xenotransplantation is 29 days. You can see here the AST, ALT, and then total bilirubin, 29 days, and blood counts on the lower panel. The platelets are red. It's, thrombocytopenia happens first few days, and then with their help, they recover it. Now the platelet counts are normal, and again, when it started failing, it started dropping, but then the animal died. They had actually 2 cases. They did 4. You can see that 2 animals, despite that they used the human coagulation factors to stop that. In 2 animals, it failed. In 2 other, it went up. The reason for it, again, in those 2 animals, they used anti-CD40 and belatacept. The longest survival 25 days and 29 days, especially. But of course, when you use the continuous human plasma, you can have the complications that we also see in human portal vein thrombosis in this animal. So the desirable thing that you don't use this continuous coagulation factors IV. This is not published, but presented in the IXA meeting that, again, from the same group at MGH. You can see that they use so many different pigs now, 10 gene, 12 gene, 15 gene pigs. They name them differently, and the survival only limited to 14 days, and only 1 pig, actually, 1 animal, 1 baboon survived. So, again, mainly the cause of that is bleeding, pulmonary hemorrhage. So most of it is bleeding, or when they use these things, hepatic artery thrombosis, because they use external human coagulation factors. So xenotransplantation, of course, when it's happened in the clinic, it could be the medical revolution, and then we published this now almost 10 years ago, and then once we publish it, the independent newspaper, and as well as several newspapers in India, published similar figures that the pigs can donate many organs and tissues. And after only 3 years, in 2015, Nature published a similar figure, and at that time with a little bit more update that the pig cornea transplant happens already in China, that islets transplant happened in the phase 3 trial in Australia, and then liver and kidney and heart and lung. So of course then others saw the impact of it. The economists put the economical impact of genetically engineered pigs. That time the editorial came in Nature Biotechnology that xenotransplantation is the second phase now. And of course, the title was Xenotransplantation Makes a Comeback. This was 6 years ago, and the Science magazine in 2017 put on the cover the CRISPR pigs. And most importantly, I'd like to show you this, that now from the scientific journals, we came to the normal humans that read the New York Times magazine. So they put this, so everybody, the normal people can read it, that 20 Americans die every day and pigs can save them. And again, another one that it's not scientific journal, it's just a normal journal that put this, that organ shortage will soon get worse. But I think this is the most important. It's not a question of if, it is just a question of when. So everybody knew that it would happen. And we show these survivals with the longest, with islets, normal cells. Of course, when you use tissue, it's much higher. When you use the orthotopic organs, the solid organs, it is actually less. But things change. In 2020, you can see that orthotopic heart came to 3 years, kidney goes to almost 2 years, orthotopic heart 6 months, liver and lung, it's the most difficult ones, but still 4 times longer than the previous ones. And even 2021, the kidney now, solid organ kidney, went to almost 3 years. And then these articles came in New York Times again last year that the kidney was attached to human. This was a diseased body, just as a trial for a couple days for heart circuit rejection, and then folks picked up immediately that it's a big step forward solving the organ shortage. And then you may have seen probably that then the first in men trial happened, heart xenotransplant from 10 gene altered pig transplanted. This gentleman was 57-year-old and very sick patient and cannot be transplanted in human. So they actually, the package was that this was a compassionate use approved by FDA, and the genetically engineered pigs was used for the first time. At the same time, the immunosuppression protocol was special. It was not FDA approved, only used for this gentleman. You can see here the pig heart and from the Science magazine also. And they published a report, full report, a couple months ago in New England Journal. And you can see here the protocol and the timeline. The xenotransplantation happened, and the patient came off ECMO, and then problems happened, and the first biopsy, second biopsy, everything was good, third biopsy, and then the withdrawal of spore. But you can see here troponin, the heart starts basically going up, it was coming down, and then most importantly, the IgG, IgM antibodies started also coming up day 45, and immunological issues start happening, and then that's why then the patient survived only 2 months. The future, it's actually bright, and with technology, we can swap the HLA, make the swine leukocyte antigen to human leukocyte antigen, so you can create the personalized pigs. This will be good, not for acute failure patients, but patients in the chronically waiting in the transplant list. And again, exciting developments in xenotransplant happens. 3 years ago, the FDA approved skin xenotransplant started. in clinical trials. Again, we have heard a couple happened, compassionate use or disease body, but the clinical trials are expected to start next year or so. And meanwhile, just last week, some new development happened that in animal testing, that it's a bipartisan bill passed in the United States is an FDA Modernization Act, the urgency to reduce and replace the animal testing. So, and then they also want this cell-based testing, because every year only in the United States, more than 100 million small animals are used in research. The economical impact is huge just for animal purchasing, and almost 40,000 monkeys and dogs in biomedical research. Again, this is, they say that they capture only 90% of it. And sometimes, you know, you're in a big lab and you use all these animals, they cannot, a private lab, they cannot capture it. So again, I started in my lab using 3D bioprinting in xenotransplants to overcome this problem 6 years ago, and published this article 3 years ago. How we use it briefly, next 2 minutes I will show you. We start with the cell base, mix the different cells to create organ models, make the cell balls, and bioprint them in temporary microneedles. It's a scaffold-free technology, and we basically, within 5 days or so, we have this freestanding tissue. And so, little video on how things look. You can prepare these in 96 wells, the cell balls, spheroids, organoids, and print them. This is a special bioreactor we created. It's a camera port, and you will see in the camera port, this is a genetically engineered pig liver bioprint. We did it in our lab, and we published this in scientific reports. You can see that here the cell balls printed, and a little faster, in 20-25 minutes we have the model, organ model, that we can actually perfuse it. So a very close look in the pig liver model bioprint. You can see these cell balls printed day 1. They start fusing, make their own extracellular matrix. By day 5, they are ready. And then now you can slide off of the support, temporary support. You have now freestanding tissue. This is a naked eye taken by my phone in 5 days. Again, you can do stack bioprinting. This is day 5 again, fused, made in own extracellular matrix. Again, microchannels, and by day 5, freestanding tissues. We perfuse these livers and organ models, and then the good thing is that it's a scaffold-free, contained genetically engineered pig cells, so that's why genetically engineered pig liver model, it continues to perfuse that time for 1 week, and then it's 3D bioprinted bioreactor we have, and of course it was very time. It saved us very important time and also budget, because it was fast and we don't have to do the pig physically each time we do the genotype changes. We are doing more in the genotyping, genetic engineering. So it's from a triple knockout, we went to 5 gene knockout, now SLA knocked out, in order to prepare ourselves also to express the human leukocyte antigen as well, but also for immunological privilege. Beta-2M is knocked out. And most recently, last month, we published these the 5 gene knockout expressing human HLA-E, HLA-G, in order to obtain NK cell tolerance, because HLA-E and HLA-G are expressed by the human placenta, female placenta, and then actually protects the fetus from not rejected by the mother. We overexpress these in the pig cells, human HLA-E and G. You can see that we can reduce this is NK cell degranulation very, very significantly compared to just 5 GKL. We can have the much better, but even though you overcome the problem with antibodies, you have now the cellular issues, and it is much better NK cell mediated cytotoxicity that we plan to also incorporate these genetically engineered pigs. We also look at the porcine ULPP1 ligand to disrupt it, so that these genes do not, the NK cell, human NK cells will not recognize But this is the most important ligand that we all know in the literature with the human NK cell interaction, but it didn't work because probably NK cell has a different ligand. You can see here with the knockout of the pig ULBP1, it didn't change. It was similar. And here also another assay, calcium cytotoxicity assay, you can see that there was no statistical difference between wild type 5-GKO. So the cellular, they bypassed of course, the antibody issues. And then, but if you express HLA-G here, just we tested it, this is much better for NK cell toxicity. So cell pathway and then antibody pathway completely different. We are now modeling livers with 5 cells, not just 3 cells. We are up to 5 cells. You can see here in different conditions. They are all viable. Look at their viability also in these liver models with different functions, as well as these are all cholangiocytes. They're the most difficult cell line to keep up with other cells. So these are all cholangiocyte markers. They were all there. So we were very happy. This data is unpublished. We published in Organoid Spheroids a model to study also different liver diseases, cholangiocarcinoma, hepatology, showing some examples, and as well as in the real world what we have done. Again, in conclusion, the future of organ transplant is actually bright with xenotransplant and 3D, eventually in the very long term, 3D bioprinted organs. We are right now doing only a model. So there is no need to discuss then the organ trafficking, and you will have unlimited supplies. And if one day you can print with the self cells, 3D bioprinted organs, then you don't even need immunosuppression. Again, every journey begins with an inspiration. My inspirations are Dr. Starzl and most importantly, Dr. David Cooper, my lifelong mentor from in the Xeno lab in transplant immunology. And I am finishing with this sentence of Dr. Starzl when he first started liver transplant. History, it was said 40 years ago, history of medicine tells us that the procedures that were inconceivable yesterday and barely achievable today often become the routine of tomorrow. Thank you very much, and I look forward to your questions.
So, thank you, Dr. Exer. Can you hear us? Can we have him on the
Yes.
screen? So great talk, and we could see a huge amount of publications on xenotransplantation, and you took us on a wonderful journey. And I think this year has been exceptionally great, especially the pig heart transplant to the human, and the heart surviving for 61 days, as you showed. And there was a comparison that the first heart allograft survived for 18 days, and then the patient actually didn't die from immune-related issues, but he died of pneumonia. And the first xenotransplant survived for 61 days. So that's a huge leap, and we're looking for exciting time. So,
Dr. Exer, most of the time we have spoken about the acute issues happening in the immediate period, but in the xenotransplant, the major criticism comes from we don't have adequate knowledge and experience to know what happens later in the immune complex front, cellular immunity, late rejection. All this we neither have evidence and nor have prediction models. What will happen to those? So when we look at the, it's true that organ pool will expand. At the same time, in organ transplant, we are looking for longevity. So do we have a clear evidence or prediction model to say that, let us say we tackle the problems now, what the acute problems or humoral immunity issues, the graft is going to survive. Do we have evidence or prediction models?
We have some evidence, definitely. First of all, I should say it's good examples of the first heart and the first in allotransplant and first xeno is surviving only 18 days and 60 days. So now we are so used to success, right? You do in India so many living liver transplants, and then first year survival is 90%. I mean, so we are used to all these successes that anything fails in these, if you think the evolution of it, the pigs and the human, you say, oh, only 60 days, we cannot do it. But we forget the past. This is how it started in allotransplant as well. So the evidence you ask, we have now 3 years of kidney xenotransplant survived in a monkey. So those of you, if you have done any monkey research, it is very difficult. The animals are actually dirty to keep it off of infection. The maintenance of animals are very difficult. They don't take medications. So you need to put, I work with them, so you need to put a very long central line so you don't have to sedate them each time to give there's very long lines, central lines get infected. So, and animal rights, I mean, you cannot keep operating. Think about the human, that you have complications, you can do surgery, and fix the problem. In animal, one complications, then you're done. The animal rights, you need to euthanize the animal. So there are so many difficulties in animal research, in large animal research, and I showed you it will be even more because this bill passed that you cannot use so many animals and so much expense. And if I pick up small animals showing that, oh, I have 5 years survival in rats, they will say this is not translational. You have to go to large animal model and then do that. Again, there are so many hurdles, but I believe many more labs now, not just single lab, different labs over the, actually over the world, I would say, in Australia, in Europe, showed long-term survivals in xenotransplant that finally the attention goes to the public, not just the scientific, like among us, that we read nature, we read science, we read New England, but the other people read magazines, internet. They don't go to these scientific journals. So now the news started coming in the normal media to the public. So the publics are they are getting ready. So I think we will see clinical trials soon in selected, of course, patients. Still, there's concern of this. We don't know if the solid organ. There will be some zoonosis, infection transfer from animal to human. For many years, everywhere in the world, we use the pig valves and no infection has been seen. But still, they think that these are decellularized in the huge organ, it can happen. So I think limited kidney xenotransplant will start and we will learn from that.
One more question is, most of the xenotransplants actually happen in patients who are really sick, otherwise do not have a long-term survival. So is it a solid reason that we are getting bad results? Because in actual transplant scenario, we'll have, even if with no transplant, they may have some months to survive. Here we have a situation where xenotransplant done in patients who are only days to survive. So what is your opinion on that? Yeah.
Well, that's a very good question, and that's discussed now. Every time we do a international xenotransplant meeting, we invite FDA folks. It's a special session, and we also raise these concerns. Each time it's very sick patients, and then suddenly the media and the public's attention or their thinking would be different. Like you said, well, it's a failure because we chose maybe the very sick patient. I think in the large clinical trials, we have to overcome that problem. And maybe if you do kidney transplant and if there's a failure, you take the kidney out and the patient still survives, then the public can think differently. Again, at the end, even though FDA people will approve this, NIH will approve that, at least in the United States, I believe similar agencies in India, they are all people. I mean, we are impacted by all these news agencies, right? So our thinking is sometimes impacted by public instead of just scientific findings. So I think in the future, this will be much better with the larger pool, but you're 100% right. So it is difficult at this time because we are used to really good success and we don't accept now the failures.
Yeah, Dr. Bhusin, thank you so much for a very enlightening talk. Maybe the public perception will drive the government to make laws which are more friendly to animal research. You never know how it works. So on behalf of the Indian Association of Surgical Gastroenterology, we thank you for joining us online. Maybe next year, who knows, if you are up to it, we can get you over right here.
Yes, this year, as you know, they opened these face-to-face meetings, and I already had so many. And I've been to India once, and I really wanted to come and be with you guys. But next year, I hope to visit. And thank you again for your kind invitation.
Great to have you. Thank you so much.